on a very fundamental level, physics is all about, classical physics at least, is all about studying the interaction between mechanical things. So, you know, levers and fulcrums. In this sort of case, you know, what can happen if you don't follow the rules and regulations of the way levers and fulcrums work. But I'll just stop that. I escaped me out of it. I want to talk a little bit more serious stuff here at the moment, and just to talk about what we offer here at CSU in the way of physics, and perhaps why you should do physics. You know, why, and I'm not trying to why has this jumped to the next thing? It's not supposed to. So you can see we offer now quite a big range of physics. The ones on the bottom of the list have only come in the last, the 299, 301, 302, 304 have only come in the last few years, and I've been sort of working on those in collaboration with another fellow from physics, and our idea is to provide a stream that enables you to do a major in physics if you want to. Now, our areas of research happen to be at the moment in astrophysics and quantum mechanics, actually a combination of the two. So that's why this is biased towards astronomy and relativity and so on, simply because that's our research area of interest at the moment. So, just to sort of give you an indication, I mean, everyone has come here and said, oh, you should do physics, or you should do science, you should do my subject in science, and look, I fully support everything they say, and I'm not here to try and, you know, sell physics over some of these other subjects, because you guys are all in the room for the right reason. I mean, you're all here for science, and I think everything that we kind of do in science is really so important to the survival of the human race and to the progress of the human race. And I mean, a lot of politicians and a lot of naysayers kind of deny some of the major problems that we're facing in things like global change and so on, you know, climate change and so on. So I think it's really important that we produce scientists and good quality scientists, and scientists that are capable of making arguments to the general public and ones that they can understand and appreciate. And again, we don't really want to be sort of pushing this as a doomsday scenario, but it really is important that we kind of approach these problems in a significant way. So what we offer at CSU is some service course physics. I don't know whether there's anyone here doing 107 at all, is there? So probably not. So I don't know.
One of the grade schools, no?
Yes. Yeah.
So students may.
Yeah. So most of you will be doing PHY 101, which is mechanical and thermal physics, and then going on to doing PHY 102, if you want to do something in physics, that is. I would recommend, and I'm not trying to push physics over other things, but one of the things I find when I look around at what's going on in the net at the moment is that when you look at jobs and the way people are working, physics underpins all the other sciences. So it explains the sort of what's going on in biology, and it explains what's going on in chemistry, and it explains what's going on in microbiology. So inevitably, if you go and see a research lab, you will find that there will be, maybe if it's the research labs in biology, you'll find somewhere there might be a biophysicist involved, simply because science has become so complicated that it's not possible for an individual researcher to know all the fields of biology and then know the physics behind it as well. So there's a lot of job opportunities in physics that are kind of related to physics, just the same as we saw for the microbiology and for Ken's work in statistics. There's so much a range of topics, and in fact where theoretical physics finishes and mathematics takes over, applied mathematics takes over, is a fine line. So you could do a PhD in theoretical physics, and then as your job you might find later on that you are making models of the way bushfires spread. So the skills that you learn in theoretical physics then enable you to produce models which can accurately predict the way a fire is going to go, and that's going to save lives. So there's a lot of really important things that physicists do that kind of don't have anything to do with physics later on in life, or not directly. So, but again, I think if you're going to do physics, or if you're just going to do a science degree, you need some fundamental basic physics. And 101 is mechanical and thermal physics, so basically what I was talking about before in the earlier video, what I was talking about or what I'll go on to talk about just really quickly, is to do with heat transfer and so on. You know, why is the Earth heating up? You know, why does carbon dioxide behave like a blanket and make the Earth hotter? You know, why shouldn't it just radiate out into space and everything stay the way it is? In 102 then we go on to talk about electricity and waves, and that's significant because, well, you know, electronics and so on is so important. IT and everything is all fundamentally underpinned by that physics that that relates to electricity and electronics. So in the second year courses, what you can do, you can actually do electronics as a second year subject. It's a fundamental electronics course. It's not going to make your head of Sonny or anything, but it's designed as a stepping stone to give you some general indication of how physics relates to electronics. More importantly, and I think this is perhaps one of the most important courses that we offer in physics, is modern physics. So often in fundamental physics courses, people only offer mechanical physics. But modern physics is really what physics is all about. Now, modern physics is the physics of the last 100 years, and I personally believe that we should try and incorporate, and we may do this in years to come, modern physics into the first year stream. So things like quantum mechanics, things like astrophysics and so on, those are sort of subjects that have come around, only come around in the last 100 years, general relativity, and they are really, really significant. They're a significant part of fundamental physics, and so we deal with those in modern physics. And if you do anything on the net, you realise that there's some just really, really strange things that go on. You know, I don't know how much any of you guys have read about things like quantum connectivity. Who's read about that? Anyone read about? A couple of people? Okay, so the idea now, just to give you an example, because I really think it's quite amazing. You will know with light, you can pass light and have it maybe go through, when you look through a window, you can see outside the window, but you can also see a reflection of what's inside as well. So in other words, what that mirror, what that piece of glass is doing, it's allowing some of the light to go through and some of the light to reflect. So that actually happens on a really, really fundamental scale. What we can do now in physics is shine a photon, which is just a little light particle basically, onto a mirror, but it's just like a piece of glass. Half of the photon will essentially go through and half will be reflected. Now in quantum mechanics, that's a kind of a real no-no. You can't have half a photon. Not only can we do it with photons, but we can actually do it with particles. You can fire a particle into the equivalent of a piece of glass. It's sort of a piece of glass for electrons, as it were. The electron can come through, and part of the wave function that describes the electron will go through the slit, as it were, and part will get reflected. And what you end up with is kind of half an electron here and half an electron there, and you say, well, that's nonsense, you can't have half an electron. And that's quite correct. But the thing about this is, it is actually extremely real. If you actually try to look and see where the electron is, so I'll look over here, I'll do a measurement to see if the electron's there. You may see it, in 50% of the time you'll see it, and in 50% of the time you won't see it. Let's say you do see it, suddenly you've got an electron there. Suddenly you've made one electron out of half an electron, or at least the wave function that describes half the electron. What's happened to this electron over here? Well, the answer is it's disappeared. So once you measure the electron over here, this electron has completely disappeared. If you do it over here and happen to find the electron here, you kind of force this one to disappear as well. So even though these things have gone off in opposite directions, they keep some connectivity between them. And people say, oh yeah, you know, when you detect this one, it's sending a message over to this one to tell it to not exist anymore. But in fact, people have done experiments now, and if there is a signal between the two, then that signal has to travel at something like 1,000,000 times the speed of light. So we believe now that these are actually connected systems. So they're almost like part of a, you know, you could imagine a wave on the sea and imagine it hitting an island and part of the wave going off this way and part of the wave going off that way. It's the same sort of thing. So you've got all these crazy things that happen in quantum mechanics, and I just sort of mentioned that as an example. The other thing I'd like to just mention really briefly, how am I going for time, Celia? Am I nearly? Yeah? I think I talked a little bit, and this is very difficult to see, it's too small to see, but again, it's kind of the same sort of thing that, no, it's gone on to the next one. All right, well actually I can probably just do the next one anyway. These are the sorts of jobs, again, applied research. You can get into forensic science, you can get into electronics, aviation, astronautics. Oh, I'll try again. I was just casting my mind back to some of the people that I've sort of worked with over the years that have done PhDs, either with me or someone else, and the jobs that they've gone into. So one person comes to mind, is now working at ANU improving solar cells. So they're making solar collectors and making them more efficient. Something, again, that we're obviously going to need in the future. Another person went over to DSTO and is now working on code breaking. So again, these were all PhDs in physics, and just the same as mathematics and a lot of these other areas, they all overlap. So you can get a job in kind of any area that you like, but I guess you've got to fundamentally like the puzzle solving, which kind of brings me to one other little quick thing I was going to show you. Just the same as John said, I think, when he gets up of a morning, he can't wait to get to work. And when I did my PhD, I really didn't know what to do, and the opening was there to do it in an area of plasma physics, and I thought, oh, I don't want to do plasma physics, you know, sort of gases, and, you know, it just didn't seem to be very exciting. But every day I got up, and I sort of got forced into it, so I went into that area, but every day I could not wait to get to work. When I was in the shower, I was thinking about, today I'll do this experiment, and this is going to tell me this, or it's going to tell me that. And I'd go there, and I do the experiment, and something fundamentally different to either of the two things I thought about in the shower happens. So, you know, I could say it's like doing a crossword, but it's much more than doing a crossword. Every day is a puzzle to solve, and every day is an excitement. So just to give you a quick example, I've got a tube here. I don't know whether you can kind of see through so I can't show all of it at the same time, but if I look at you should be able to see that the tube's hollow. And two of these little discs, the tube's made of copper. This one's made of copper. This is actually a magnet. Quite a strong magnet, but as you know, magnets aren't attracted to copper, or copper is not attracted to magnets. But nevertheless, if I drop an ordinary piece of, so this is the copper one, if I drop it through, it just sort of falls at a normal rate, just the same as if you dropped it just like that. But if I take the magnetic one, something really interesting happens. I'm going to drop it, doesn't hit the side. In fact, it hits the side less than what that one does. When I drop that one down, you can kind of hear it. Oh. You can hear it hit the side on the way down. But this one doesn't hit the side. Not only doesn't it hit the side, but you can see that it's sort of feels like it's almost got stuck. If you came and had a look down the top of it, you can actually see it going down like this, floating from side to side. And just before it hits the side, it floats away again. Something, as it tries to go, and there it's come out at the end now. So the question is, why? I'll just do it one more time while I talk about it just a little bit more. And so this is the sort of thing, this is the sort of puzzle that you get doing science every day. And I could say, oh, look, you only get it from research, but any area you go, you come into the same sort of problem. So if you, even with a BSc, you're kind of working in areas you might be working with people that, research scientists that have PhDs, or you can go on and do a PhD yourself, but you don't have to. You get to work in labs and do this kind of exciting stuff where new stuff is happening all the time, and it's really tremendously rewarding. I can say that it's probably, you know, sort of going into this area and the career choices that you are going to make now, and I guess I'm preaching to the converted because you already want to be scientists, you know. So, but nevertheless, I really do believe you guys are on a very, very exciting journey because, as I said, even areas that you don't think are going to be very exciting, like I didn't think plasma physics was going to be very exciting, turn out to be really, really great. And I think that would be the case in any area you went into, because it's the solution of the puzzle that makes the whole thing exciting. But anyway, I might just leave it there. I don't know whether it's, yeah, so...
Do you guys have any questions for Adam?
Just before I do, I'm going to show them one more thing. This is actually something to do with robotics, and it's actually old news now. It was out in 2010 or something, but quite incredible what they can do with robotics these days. Unfortunately, it's a little bit military, but assuming it's going to work. This is a thing they call a big dog. It's made by Boston Dynamics, who works for DARPA, who's kind of, you know, not that far away from waterboarding and the CIA. But anyway, the important thing is that to show you what this thing's all sort of self-contained, and it actually looks like, I reckon it looks like two guys with their heads back to, but it can really do some amazing things. And it's not just for military. I mean, they can send these things in there saying where firefighters would have once been killed, they can now send these things in to carry payloads, carry water in, all this sort of stuff, and they've now got a one that they call Atlas, which you might have seen, that actually runs around and actually behaves like a human being. These things, when they fall over, they can pick themselves up again. Yeah, that's a bit of a joke. But anyway, so but it's just, I just want to show, so, physicists, this is what physicists do. Physicists design this. There'll be a whole range of physics people working on this. There'll be electronics people, there'll be, where does one science stop and one science start and one science stop, but as I say, I just don't know how much longer this is. It's not long. We might as well let it go till the end. So obviously this is showing the military uses of this thing, but there's a lot of other useful areas in society that this can be employed. I think this one actually runs on petrol, but the newer ones run on batteries. So there you go. Anyway, I just thought I'd show you. It was just a little interesting. Yeah, so you can see their funding and the obvious applications.